Hi everybody, we're today going to look at something called the Zeeman effect, and this is a particularly interesting topic of discussion. What we're going to do is we're going to follow through our rules for quantum mechanics and actually think about the classical behavior, the classical physics behind the application of a magnetic field to a hydrogen atom. And we're going to start to see how we can modify the Schrodinger equation to account for that magnetic field. So lots of classical physics to start with here, and then we're going to find quite an interesting explanation of the spectroscopic observations that we see in reality. And later we're going to move on to start thinking about electron spin of electrons, and all these things are connected in what we call the Zeeman effect. So enjoy. Okay, so let's look at the Zeeman effect, and this is taken from section 7.4, and that is the section titled Energy Levels Are Split by a Magnetic Field. So we're going to imagine that we have an electric charge that is spinning around in a loop, and the circumference of this loop is of course 2 pi r. So we have this motion of electric charge around a loop, and this motion produces a magnetic dipole. And that magnetic dipole we're going to call M. Now the magnitude of that magnetic dipole is given by the following. So the magnetic dipole M is equal to I multiplied by capital A, and I is the current in amps, and A in here is the area of the loop. And what would you expect the units to be? Well, of course, that would be meters squared for the area. What else can we say? Well, what is current? Well, current is equal to flow of charge per second. So we would expect it to be dimensionally associated with charge over time. And indeed, in this particular case, the current is equal to the charge multiplied by the velocity. So we have that electric charge moving around the circumference of the circle. And so in the denominator here, we're going to have 2 pi r. And of course, what this ultimately means is velocity is meters per second. So the what we're going to have is coulombs on the top here, and then meters, and that's going to be meters per second. And then also we're going to have the units of circumference is also going to be meters, so these cancel out, and so we end up with a current which is charge divided by seconds, so charge over time. That's our current. Of course, we also know that the surface area of the loop is equal to pi r squared, and that unit of course is also going to be it's going to be in units of meters squared. By the way, why do we care about this? So let's just put some context around this for a second. Let's just remember that magnetic field causes energy levels to be split into sublevels. So in other words, we can see a split in spectral lines. Okay, so this is the Zeeman effect. So all our experimental observations are done in spectroscopy. So that was the context. Let's come back here for a second and again recognize that the magnetic dipole is equal to our current multiplied by the area of the loop. So that means when we bring these two equations together, we get M is equal to QV over 2 pi r, and then we multiply that by our area of the loop, pi r squared, and this comes out to be Q times the velocity times the radius, and that's over 2. So the pi cancels and the r cancels, so we end up with QV r over 2. Now in the event that this motion does not take place in a circular orbit, we can also write this in terms of vector quantities, and in this case we bring in the cross product of r and v. And next what we're going to do is recognize that angular momentum, so the vector for angular momentum, is equal to r cross p, so that angular momentum also becomes as shown. There's the cross product in here. So what we can do is substitute, and now we end up with a vector expression for the magnetic dipole. In other words, L over M is equal to R cross V. Okay, if we now think about how we're thinking about an electron, so the charge here is equal to minus the fundamental charge, and so we're now going to plug this into our expression. We end up with the magnetic dipole is equal to minus E times the angular momentum over 2 times the mass of the electron. So now we have the mass of the electron as denoted by this subscript. We also recognize that this magnetic dipole is perpendicular to the plane of motion. Again, what we recognize is we've got this circulating charge, and the dipole moment, using the right hand grip rule, is pointing upwards when the electron is moving in an anti-clockwise direction. So just like a dipole moment interacts with an electric field, just like the dipole moment of a molecule interacts with an electric field, so a magnetic dipole also interacts with a magnetic field. So let's make a note of that. And we also introduce the idea that the potential energy of the dipole in that field is given in the following expression. V equals minus M dot product this time multiplied by, or dot product with, the strength of the magnetic field. And the units for the strength of magnetic field are the Tesla. So we also have to define the strength of the magnetic field. It is defined as follows. So it's defined through the force felt by a charge with velocity of v. So this is a definition. Definitions represent things that we do pull out of a hat. So we're making progress by making these definitions. What we can do now, though, is resolve this in the z direction. So in the z direction, that potential energy is equal to minus m sub z times the magnetic field strength in the z direction. So no longer vector quantities, because these are now in the Cartesian coordinates of the z direction. And we remember from before, this is actually equation 7.37 from Quarry, and that is, we've written that already, that this magnetic dipole is equal to minus the fundamental charge multiplied by the angular momentum over 2 times the mass of the electron. And we're going to substitute this in. Let's change colors for a second. So we're substituting that in. We end up now with V equals, so here's the potential in the z direction. So now we have that potential, and you'll notice as well that we have our angular momentum term in here. So what this allows us to do, remember that this V is a potential energy, what this now allows us to do is think about if we wanted to adapt the energy of our system quantum mechanically, how do we do that? How do we go through the process of describing the system classically and then going through the process of going quantum? What we can do is we actually replace this L sub z term with the quantum mechanical operator for L sub z. So we can build a Hamiltonian operator that accounts for the impact of the external magnetic field. So how do we do that? So our new Hamiltonian operator is going to be equal to our original Hamiltonian operator for the hydrogen atom, but now we've also got this additional term. And remember, our second rule after we've determined the classical physics of our system, then we start to replace certain observables with their quantum mechanical operator. So here's the operator here that we're going to introduce. And H naught in here, in fact it's H naught hat, is the Hamiltonian operator for the hydrogen atom. And we know already, by the way, that psi is an eigenfunction of this Hamiltonian operator. We've demonstrated that earlier in the chapter. We also know that it's an eigenfunction of L sub z. So this means that all these wave functions are solutions. If it's a solution for the Hamiltonian operator for the hydrogen atom in here, then it must also be an eigenfunction separately for, we know, for L hat squared and for L hat z. So this is pretty important here. What else do we know from earlier in chapter 7? Well, we know the eigenvalue for the Schrodinger equation for the hydrogen atom. So let's have a look at that. So our eigenvalue is already known. And similarly, we can do the same thing when applying the quantum mechanical operator for angular momentum in the z direction to that same wave function. So this means we can easily rewrite the Schrodinger equation, but now we can collect the eigenvalues on the right hand side, and those will become the energies of that hydrogen atom that finds itself in the magnetic field. So let's have a look. So now I'm highlighting in red the piece that comes from the operator equation in the previous line. And what this means is that we have a new eigenvalue. In other words, the energy of that state, the energy of that hydrogen atom while in this magnetic field, is exactly this eigenvalue. What I'm also doing right now is I'm going to define a new term called the Bohr magneton. And we have to be careful here because this is the beta term in this particular expression. And that Bohr magneton is defined as the fundamental charge multiplied by h bar over 2 times the mass of the electron. And the numerical value is as follows. That is 9.2740 times 10 to the negative 24, and that's joules per Tesla. Joules per Tesla. So what does this all mean? It basically tells us that a state with given values of n and L is split into 2L plus 1 levels by a magnetic field. So the two p orbitals are split by this magnetic field as shown in the diagram below. So here we have a p orbital, and since L is equal to 1, that means it's split into 3 different levels. Of course, an s orbital, L is equal to 0, so that would only be split into 1 level, and therefore it wouldn't be split at all. So this is something that happens to p orbitals and d orbitals. And what we've done is we've demonstrated how we can extend the Schrodinger equation for a system that classically has a change in the energy, and we've actually fit that into the Schrodinger equation, and we've used that Schrodinger equation to help us understand the splitting and in fact the experimental spectra that we see in the real world. So we're now going to move on to electron spin, but thank you for listening to this section.